Hi students, welcome to physics. Today we're going to have an overview lecture for chapter 3 of your textbook, which is about accelerated motion. I'll try to make it brief, and please note as we're going through this first lecture, there'll be a lot of content and I'll go relatively quickly. And this is meant as an introduction. We'll talk more about the details as we go through the unit. So this is pages 58 to 81 of your textbook, which is a PDF at the bottom of the unit for Unit 3. Section 1 of the textbook and Section 1 of this lecture goes through a definition of acceleration. What is acceleration? How is it different from velocity? And what information can we get about acceleration from velocity versus time graphs? We've got some vocabulary, vectors, and scalars. We're going to have a definition for acceleration and average acceleration and the difference between average and instantaneous acceleration. And then, of course, reviewing what a velocity versus time graph is. So in the previous unit, we were focused on uniform motion. And uniform motion means motion with a steady speed. We looked in the end at motion that was uniform in pieces. So we would have something going at a steady speed for a while and then going at a different steady speed for a while, sometimes even turning around. But in each of those sections, the object moved at steady speed. Now we'll start looking at motion where an object has a speed that is changing all the time or accelerating. In our everyday use of the word acceleration, we usually mean just something that's speeding up. And we use the word deceleration for something that's slowing down. Acceleration can occur when an object speeds up or slows down, but it can also occur when an object changes direction. Velocity is a vector, so it has a how fast and a direction. And acceleration is defined as how much velocity changes divided by time. So an object can accelerate if it speeds up, if it slows down, or if it changes direction. Acceleration is measured in units of velocity, meters per second, divided by units of time, seconds. So meters per second is the SI unit of acceleration, and we abbreviate that as meters divided by seconds squared. We will look at motion maps, or your textbook calls them motion diagrams. And a motion diagram for an object that's accelerating should show different distances between the dots. So here's a girl walking forward with a steadily increasing velocity. We would see snapshots of the girl where the distance from one snapshot to the next gets bigger and bigger. If she were slowing down, we'd see the reverse. The distance between snapshots would get smaller and smaller instead. We're not going to worry too much at the moment about finding an acceleration vector direction from a motion map or a motion diagram, but this reminds us that acceleration really has a direction, and instead we'll focus on the kind of rule of thumb of acceleration direction. So if an object is speeding up, if an object is, using our everyday term, accelerating, then acceleration and velocity point in the same direction. Velocity vector is getting bigger and bigger. If an object is slowing down or decelerating in our everyday use of the word, the velocity vector and acceleration vector point in opposite directions. The velocity vector gets smaller and smaller. And so we'll just focus on this rule of thumb. Speeding up has velocity and acceleration pointing in the same direction. Slowing down has velocity and acceleration pointing in opposite directions. So we look at a velocity versus time graph. In the past, up till now, we've looked at objects whose velocity is steady, at least piecewise. So we had flat horizontal velocity versus time graphs. And sometimes we would see a velocity versus time graph that looks like stair steps, meaning that the velocity was steady for a particular amount of time and then steady at a different rate for a particular amount of time. Now we're going to consider objects whose velocity are always changing. So here we have a graph of an object that starts with 0 velocity, and its velocity steadily increases as time goes on from 0 to 5 seconds. So every second, this velocity increases by 5 meters per second. I can see that as the slope of the green line. So that tells us that the slope of a velocity versus time graph is the acceleration. Slope is rise divided by run, which is, in this graph, increase in velocity divided by time interval, 5 meters per second every second. So when we're looking at a velocity versus time graph, the slope of that graph is acceleration. Of course, acceleration doesn't always change steadily, as in the previous graph. Acceleration, particularly if we're thinking about a car with an internal combustion engine, acceleration changes as time goes on. Acceleration and the torque of the engine change as the engine's rotation speed changes. If you know about cars, that's fine. If that doesn't make any sense, that's fine too. However, we are not going to worry about finding the acceleration of an object whose acceleration is changing. We are only going to be finding average acceleration. So like average velocity, average acceleration only depends on the end and start of the velocity, not how the velocity changes in the middle. So acceleration is change in velocity divided by time interval. And we're back to that delta notation here. Delta, Greek letter D, looks like a triangle. And whenever I write delta something, I mean change in. So change in velocity, or the difference between final and initial velocity, divided by change in time, the time interval, the difference between ending and starting time. So here's an example. Here's a velocity versus time graph that changes wildly, right? The velocity versus time here is not steady, not steadily changing, but we can use this graph to find average acceleration. So what's the object's average acceleration between 20 and 40 seconds? So we find the velocity at 20 seconds. So I read the graph, I look at 20 seconds, and I see that the value of velocity is 4 meters per second. And then I read the graph and find the value of velocity at 40 seconds, which is 0 meters per second. So the ending velocity is 0 meters per second. The starting velocity is 4 meters per second. So ending minus starting, 0 minus 4 is -4. And I divide by the time interval during that change. So from 20 to 40 seconds is 20 seconds. -4 divided by 20 is -0.2 meters per second per second. So the average acceleration from 20 to 40 seconds is -0.2 meters per second every second. We'll skip calculating the instantaneous acceleration, but if I needed to know instantaneous acceleration, I would find the slope of that graph at the point. That means finding the tangent to the graph. And I'm not sure that everyone has, in math class, discussed tangent lines. So we're skipping it. Let's see, here's another example of calculating average acceleration. On a test track, a professional driver performs a 0 to 60 test. That is, she starts the car at 0 meters per second at rest and accelerates as quickly as the car can to 60 miles per hour. 60 miles per hour in SI units is 28.6 meters per second. If the time it takes for this test is 8.5 seconds, what's the average acceleration? So again, here we find change in velocity and we divide by time interval. So here the ending velocity is 26.8. The starting velocity is 0. So we have a change here of plus 26.8, an increase in speed. We divide by time, 8.5 seconds, and we find that the acceleration is 3.15 meters per second, or again, the abbreviation is 3.15 meters per second squared. In section 2, we're interested in using the velocity versus time graph to develop a mathematical model for velocity and displacement. This will go quickly and we'll need to return to these ideas a few times, but I want to introduce you to the ideas. So first, what does a position versus time graph look like if acceleration is constant? Unfortunately, this graph has some tangent lines drawn, But if I can concentrate on the green position versus time graph below, the green line is a curve. And you might recognize the shape of that curve as a quadratic function. So when acceleration is constant, position versus time is a quadratic function, y equals x squared. And of course, as we've already discussed, the velocity versus time graph is a straight line when acceleration is constant. A straight line either pointing up, positive slope, or pointing down, negative slope, meaning a speed up or a slow down. So if we want to switch the velocity versus time graph to a velocity function, we've done this before for position, we fit velocity versus time to a linear function, y equals mx plus b. So y equals mx plus b switches to not y, but v, velocity, equals mx, becomes acceleration times time. The m in mx stands for slope, that's acceleration. And the x in this graph is time, t, plus b, the intercept. If the velocity doesn't start at 0, the intercept is the starting point. So we're switching from this red straight line graph to a function that represents that graph. Whoops, I was trying to highlight the function. There. V equals starting velocity, b, intercept, plus acceleration times time, mx. Then to develop an equation for displacement, we remember that the velocity versus time graph's area tells us displacement. This is not something I can prove without calculus, but we looked at how when velocity is constant, we find displacement by multiplying velocity times time, and how when we're doing that on a graph, what we're actually doing is finding area. So we're going to take it as accepted that displacement is found by finding the area under the graph of velocity versus time, and that's true whether the velocity versus time graph is horizontal, steady velocity, or changing velocity. So velocity with average acceleration, here's an example of what we've done in the past. Find the displacement of this car given the velocity versus time graph. Here we're going to have a rectangle, so a velocity value of negative 1.5, and a rectangle that forms from 0 to negative 1.5 height, and from 0 to 4 seconds base. So base times height, negative 1.5 times 4 is negative 6. The car has a displacement of negative 6 meters, which means that's the displacement, backwards negative 6 meters. So finally, we try to make that as broad as possible with a velocity versus time graph with a changing velocity. And so here we will need to find the area, the pink area below, which is a rectangle, so base times height, plus the green area, triangle, half times base times height. And it's not important for you to be able to recreate this derivation. Instead, we just want to recognize that this equation, displacement equals velocity times time, that's the pink area, plus half times acceleration times time squared, that's the green area. This equation for where an object is in the future came from the old idea of finding the area of position, finding the area of velocity versus time, which gives us position versus time. So looking at velocity versus time graphs, this is the big idea for this section. Looking at velocity versus time graphs, we're able to apply the straight line function to velocity versus time to have an equation for velocity. And then we're able to apply the idea of area of a velocity versus time graph to find the equation for distance or displacement. I'm being a little bit casual with those two words. We need lots more practice with these equations. And so this is just meant to be an introduction. And this should be enough to get you started on assignment number 1 for chapter 3. And I'll see you on Thursday with your many questions.